In the name of Almighty God, I'm Mahsa Sankashan. Today I want to talk about nuclear fusions models in solid states. This is not the case with many alternative receiver systems. In section 5.4, we will consider palladium nuclei as candidate receiver systems. Transfer to palladium on the receiver side instead of helium-4 is expected to result in faster rates. Since transitions from palladium ground states to excited states, palladium 10s to palladium stars are less hindered than the helium-4 tends to deuterium-deuterium transitions. In that case, while there is an analogous transition hindrance factor that we will refer to as the oxygen value section 5.4, this hindrance factor is many orders of magnitude smaller compared to the impact of the deuterium-deuterium Colombo barrier on the receiver side. See section 5.5 and figure 23. Considering a different nuclear species, system raises the questions of how to achieve resonance with the donor transition. While it is in principle conceivable that a palladium nucleus exhibits a suitable excited state precisely near the resonance conditions of 23,848,109 electron volt, such a coincidence would be unlikely. However, as will be discussed in the sections 5.7 and subsequent sections, combinations of multiple lower energy and longer lived palladium excited states result in an extremely high density of states near 23.85 mega electron volt and above, allowing for the resonance conditions to be met. In practice, other issues need to be considered, such as the effect of higher power transitions and transient of the oscillatory modes of interest, which lead to a temporary increase in coupling strength due to the dependences of coupling strength on the dissipated power in the oscillator modes. See the section 5.1. High power transient can arise from the shocks deliberately applied to the lattice, for example, to laser pulses, and also from internal lattice dynamics, for example, phase changes. The impact of such high power transient on the evolving excited transfer dynamics will be considered in section 5.6. As for reaction products working with a different nuclear species than helium-4 as receiver systems offer other advantages. With respect to observables, if the receiver nuclei were to disintegrate upon receipt of the transferred excitation, thus turning the closed quantum system into an open one, the process becomes observable. Many heavy nuclei can reasonably absorb energies near 23.85 mega electron volt and higher, and would promptly decay via alpha proton and neutron emissions upon receipt of such large quantum of excitation based on the reference 71. This final step at the end of the rather complex process of excitation transfer could then account for the reported energetic particle emissions from metal hydrogen systems, such as those summarized in sections 2.3. And even more detailed treatment of problem also recognizes that the density of states on the receiver side gets very high when allowing for energy exchange between the nucleus states and the oscillator modes, section 5.10. In that case, there is not just a single discrete receiver state, as in the idealized example of transfer from deuterium-deuterium donor systems to helium-4 receiver systems, but many possible states on the receiver sides. This, in turn, requires a golden rule treatment when undertaking rate calculations and a corresponding model. We find that rates in such a model are particularly high and argue that such a model may be well suited to connected with the kinds of the experimental reports mentioned above. Every energy exchange from the excited nuclear states with oscillator modes of the lattice when there is A high density of states that nuclear systems can traverse as they emit energy into phone and plasma modes provides an intrinsic explanation for so-called excess heat effects observed in metal hydrogen systems. In such experiments, researchers have reported the accumulation of heat far beyond the applied input energy and the chemical potential energy in the system. The discussions in this section sought to provide a broad overview of nuclear excitation transfer dynamics. A more detailed and comprehensive treatment with estimate for real systems is provided in section 5. Now I want to go through the next chapter, quantum dynamics of nuclear fusion and condensed matter detailed treatment. Section 4 laid out of a basic conceptual overview of relevant dynamics sections. Here we provide a more detailed treatment that goes deeper into individual points raised. It will present arguments for how in specific kinds of metal hydrogen systems and quantum dynamics energy transfer mechanisms in combination with electron screening and molecular like proximity of hydrogen isotopes can result in greatly accelerated fusion rates. Some of the quantitative examples in this section are idealized and primarily pedagogical in nature, seeking to help the reader appreciate different aspects of this complex problem. Other quantitative examples are based on realistic assumptions, and we argue that the resulting fusion rate estimates in the observable range align with reports of energetic particle production as well as excess heat production in metal hydrogen experiments such as the one briefly discussed in section 2. In their development, these arguments have undergone many iterations, and we expect further refinement and expansions in the future. Nevertheless, we are confident that the mechanism laid out here and their combined effects in specific metal hydrogen systems represents a viable approach to engaging with experiments reports productively. We propose that this approach makes solid-state fusion actionable not only from an experimental perspective, such as with the ARPAE program on low energy nuclear reactions that commented in 2023 based on the reference 72. See sections 5.16, but also from the theoretical and modeling perspective. As we make more progress in developing and refining these arguments, we will provide updated versions of this document and subsections of it via our groups in GitHub site at github.com/project-ada. This includes links to evolving preprints as well as computational notebooks and regularly update lists of related published materials. Now I want to go through the nomenclature and visual language. These sections will make use of figures that include schematic representations of atomic and nuclear structures. We therefore adopt different visual language to represent systems such as deuterium, helium-4, palladium-A, palladium-A star, excited states of palladium state, isotopes as discussed in 5.4. Figure 6 summarizes these visual representations at atomic and nuclear scales. We will frequently refer to transitions in this document, and its usage of this word, along with the related notations, requires some elaboration. Depending on the context, transitions may be used in a static manner, referring to the energy level spacing in a two-level or multi-level system. For instance, the level spacing between a palladium excited state, palladium star, and a palladium group state, palladium represents a transition in the sense of the word. In such cases, we use notations palladium star per palladium to denote and upper and lower energetic states of the system. Since deuterium is viewed as an excited state of helium-4 in this document, we often refer to the deuterium helium-4 transitions in this way, which is associated with the 23.85 megaelectron-volt mass effect energy that defines the level spacing. The other use of transition is more dynamic one, referring to an actual state change rather than to the static configuration of energy levels. For instance, the palladium star palladium transitions can undergo a state change when an acopite excited state decays to the ground state. In this case, we use notation palladium star palladium tends to the palladium to represent this process, and we refer to it as a palladium star tends to palladium transitions. The reverse of the latter is a palladium tends to palladium stars transition in the case of an excitation instead of a de-excitations. In most instances, the meaning of the transitions will be clear from the context. However, the ambiguity might arise. We will explicitly refer to two-level systems or TLS to indicate the state use of the term and the state change to indicate that the dynamic use. You see, Figure 6 illustrates different visual representations at atomic and nuclear scales used in this document. They are in a palladium stars can be used to refer to a specific palladium isotope, whereas the use of the expressions palladium A indicates that any stable palladium isotopes can be considered here. You see from the range, it is 74 picometer and deuterium molecule in the left side FM range, and in the left side we have a helium-4, palladium A ground states, and you see the magnification of the A palladium A star bond states, and also palladium stars A when a nuclear molecule states here, rubidium and helium-6. Now I want to go through the another chapter from a comprehensive Hamiltonian describing nuclear in a lattice nuclear decay model. The starting point for this exploration of nuclear quantum dynamics is comprehensive Hamiltonian that describes nuclear in a lattice as well as various oscillator modes that the nuclear states couple to weakly. This starting point is consistent with the Ternio and Baldwin's in reference 8 perspective, who in a 1965 physical review letter laid out a basic approach to modeling of nuclear dynamics in a lattice with a single comprehensive Hamiltonian that accounts for nuclear lattice modes, radiation, and interactions. The need for such a comprehensive Hamiltonian is motivated by them as follows. In a solid composed of nitrogen and identical two-level nuclei in a perfect crystal lattice at a uniform and low temperature, correlations in the internal motions of the radiators are more probable than in the case of a gas. The usual assumptions that each nucleus radiates independently of the states of other nuclei in the system is compatible with the coupling of the nucleus through the common electromagnetic and phonon fields. The most generic form of the comprehensive Hamiltonian that Ternio and Baldwin provide is Hamiltonian is equal to Hamiltonian nucleus plus Hamiltonian lattice plus Hamiltonian radiation plus Hamiltonian interactions, voltage interaction. A more specific form of the comprehensive Hamiltonian used here is Hamiltonian is equal to Hamiltonian nucleus, Hamiltonian phonons, Hamiltonian pulse modes plus Hamiltonian magnones and plus voltage nuclear phonons, and also nuclear pulse modes and magnones. In this equation here, there is a Hamiltonian to account for ground states and excited states of nuclei in the system. There are condensed matter Hamiltonian for phonons, plasmons, and magnons, and there are interactions term that describes coupling between the nuclear states and the phonons, plasmons, and magnons in the system. Since such a comprehensive Hamiltonian describes a multitude of dynamics and is essentially interactable, it will be gradually simplified into sections with the goal of identifying key dynamics that, under specific circumstances, yield observable effects. For the sake of simplicity, we will start by dropping the magnitude terms. The focus for calculations in this document will be on phonons, but extensions for plasmons are discussed in sections 2.7 to 6.27. The potential role of the magnons will have to explore in the future work. The nuclei can be represented in the Hagelstein nucleus is equal to sigma j and k, and phi j mj c to the power of 2 phi j k, where the mass energies mj c2 of the different nuclear states j at the different sites k in the lattice are written in a multi-level systems notation. In contrast to two-level system notations, Piaget represents nuclear states in terms of internal degrees of freedom. The focus here will be on phonons and plasmons whose Hamiltonian are of the form of the HF phonons is equal to K nu H omega K nu to the power of phonons I K nu to the power of T and I K nu. Vector is a vector of phonon and plasmon modes. Nu is described which mode is considered, and omega k and nu is the frequency of the respective mode. When considering both electric and magnetic interactions associated with oscillations of nuclear when vibrations occur, the interactions term can be expressed via multiple level system formalisms according to the references in 74 and 75, where E is the electric field strength, B is the magnetic field strength, and D is the electric dipole operator. Micro is the magnetic dipole operator, and where J and J prime are nuclear states included, and co-indexes the sites in space where the nuclear are positions. For simplicity in these sections, we will restrict ourselves to the case of electrolytic dipole interactions. However, the overall dynamics explored here are in the principle agnostic to the type of coupling that is focused on, and we describe dynamics and provide rate estimates based on different coupling and different nuclear transitions later in this context. Sections 5.3 and subsequent sections in terms of nomenclature, we use V here to refer to coupling generically, and we use subscripts to refer to specific couplings. For example, V electric, therefore we can write here V nuclear phonos is equal to V electric is equal to minus sigma J J prime K, and phi J DE and phi J prime based on the K. Electric coupling in this context can be thought of as follows. Acceleration of an individual nucleus occurs because of the local oscillatory field in a classical picture according to the equation 23 mj. The second derivative by rj based on the time is equal to zj ek, where rj is the center of mass position, zj is the nuclear charge, and E is the unit charge. In the quantum version of the model, a position operator is expressed in terms of the different Faunus modes according to these equations, where L denotes the unit cell and where J Kanu is a phono-polarization vector based on the reference 76. J index the positions of the nucleoli is a phonon wave vector, and nu indexes the phonon branch. For example, acoustic, optical, computational, and transverse. Corresponding electric field operator can then be defined at a given nucleus positions as a function of phonon modes. Now I want to go through the another sections, focus on specially uniform traction. A first glance at the overall Hamiltonian draws attention to several critical aspects. The coupling energies in the D and micro minus micro B interaction terms are comparatively small, and the state transition energies in the nuclear terms are comparatively large. The small coupling energies have to do with the small sizes of nuclei, which limit their electric dipole moments. Large transition energies in the mega electron volt range are typical for nuclear states. Transitions are interesting to nuclear physics. Oscillator transitions, in turn, are near an electron volt and less. Consequently, first order processes, emissions, or absorptions of the single phonons, plasmons, or magnons are not expected to be important, which agrees with the basic intuition and experience because due to the large mismatch, energy cannot be conserved in a first order exchange process. However, energy can be conserved in second order processes and also in higher order processes. The focus below will be on the second order oscillator mediated excitation transfer processes. Later on, we will make heavy use of higher order generalized excitation transfer process based on the sections 5.10. Despite the relevance of excitation transfer and higher order processes, dynamics can be expected to be slow due to the weak coupling strengths between nuclear state transitions and condensed matter degrees of freedom. For example, phonons, plasmons, and magnons. However, decay enhancements based on the reference 77 can compensate for this and accelerate dynamics. Decay enhancement is expected in many body quantum systems interacting with a uniform common oscillator originally applied to the coherent or radiating gas. Its relevance for accelerating nuclear state transitions and nuclear reaction parameters we first described in 1965 and 1990 respectively. In the context of excitation transfer, decay enhancement has been referred to as supertransfer based on the reference 79, since only decay enhanced interactions can be expected to yield observable effects in the given systems. The modeling focus will be reduced to such interactions. This results in a restricted Hamiltonian of the form of the equation 26. In these idealizations, the different nuclear states interact with a single uniform acoustic phonon mode, with a single uniform optical phonon mode, oxygen, and with a single uniform plasmon mode P via electric interaction DE. The electric field operator is now uniform across all nuclei in the domain and simplifies to equations 27, where a unit vectors account for the polarization and amplitude that are involved for a specific nucleus. This model describes many multi-level molecular systems with large state transition energies collectively and uniformly interacting with three different condensed matter oscillators at low energy. As such, its state transition and energy transfer dynamics are subject to cooperative decay enhancement similar to the supertransfer collective excitation transfer dynamic described in reference 79. A remaining difference is that here we have multi-level systems and the typical decay mode works with two-level systems. We will next describe how the above Hamiltonian can be further simplified to correspond to the generalized decay model. Now I want to go through the nuclear idealized as two-level systems. Also, the model above is already much simpler compared to the starting point. Further idealizations will be helpful in the understanding the associated current dynamics if we replace the multi-level systems that describes the nuclear states with simpler two-level state system. Then we end up with idealization that is more amenable to analysis, considering a deuteron pairs such as in molecular deuteron. The different nuclear states are shown schematically in figure 7 and also in figure 3 of reference 80. The alloy states include sulfur 1, sulfur 5, P3 and deuterium 1, deuterium 5 states, all of which including sublevels can be described in an multi-level model formalisms. Note that half the cells that one may expect are missing because the generalized Pauli principle makes the constructions of antisymmetric states impossible. A more detailed discussions of the relevant deuteron states and their wave functions, as well as the relevant helium forces and their wave functions, is presented in section 6.1. A brief review of noun excited states of helium-4 in the literature is provided in section 6.4. In two-level system descriptions, as used below, this collection of states is replaced by a single generic deuterium molecule state as the excited state, a highly clustered four-nuclear configuration, and an unexcited helium-4 current nucleus as a ground state, compact four-nuclear configuration of a two-level systems. You see, we have figure 7, and it is illustrating molecular states and nuclear spin states of deuterium-deuterium molecule versus a helium-4 nucleus. The deuterium-deuterium states are effectively degenerate with rational energy, rotational energies on the order of the mega electron volt. Even parity states are indicated in blue, and odd parity states are in red. Related helium-4 star excited states are shown in the figure 47 in section 6.2. The next chapter is pseudo-spin formalism for ensemble of nuclear two-level systems are conveniently modeled making use of Pauli matrices. Here, the pseudo-spin formalism is employed so as to focus not just on a set number of two-level systems but on the collective behavior of an extensive systems of such entities. This formalism is common mathematical to describe collections of two-level systems and is named after a spin event tau. In many cases, there is no spin involved at all in the problem. For a single two-level system, the formalism based on a single pseudo-spin operator can be used according to these equations, where sigma is a vector made up of Pauli matrices, where I are the Cartesian unit vectors. A single pseudo-spin operator is useful for modeling a single two-level system. If there are many two-level systems, then it is convenient to work with a bigger pseudo-spin operators defining according to these equations. Equation 30, S is equal to sigma lower boundary is j, so j is equal to h divided by 2 sigma. Our boundary is j sigma j. This aids in the analysis of models where cooperative enhancements occur, since the associated many pseudo-spin operators leads to cooperative factors naturally. Now I want to go through the generalized nuclear decay model. We can write the two-level idealizations of the model about making use of pseudo-spin operators according to the equations 2031, where S plus J is a pseudo-spin raising operator and S minus J is a pseudo-spin lowering operator, and the nuclear dipole matrices elements are assumed to be real. The model is now decay model. In this derivation, the focus was placed on electric coupling. However, the Hamiltonian can be written in a more general form, and the different interactions we can be readily considered as we will be down in sections 5.3 and subsequent sections. Note that this decay model is similar to supertransfer models in the literature, such as equations 1 in Lyot and now I want to go through the another sections. Excitation transfer dynamic between deuterium-deuterium and a resonant receiver nuclear state. The above described decay model is cell complex containing a multitude of possible dynamics, and it can be applied to many different physics systems. Herein, we focus on resonance nuclear excitation transfer between deuterium-deuterium molecules and helium-4 nuclei, which represents excited and ground states of idealized two-level system. Per the discussions in sections 5.1 and 6.1, where molecular deuterium is viewed as being an excited state of a multi-body systems where helium-4 is associated ground states. This physical setup implies that the receiver system's helium-4 is perfectly resonant with the donor system's deuterium. To proceed this way, we consider two ensembles of nuclei A and B, whereby ensemble of on denotes the group of deuterium-deuterium nuclei and the coupled systems which can undergo the deuterium-deuterium tends to helium-4 transitions, and B denotes the group of helium-4 nuclei and the coupled systems which can undergo the helium-4 tends to deuterium-deuterium transition. Note that the collective transitions of group A occurs coherently together with the corresponding transitions in group B, also intermediate, sometimes referred to as virtual states, are involved, as will be discussed later in these sections. Our starting point is generalized nuclear decay model, equation 32. Recall that the corresponding Hamiltonian based on first order coupling between the nuclei and oscillator model is based on the equation 34. Again, for the sake of simplicity, the following 5.1 we focus here on electric coupling. This reduces the drawing expressions of equation 32 to equation 31. We can denote this as Hamiltonian is equal to Hamiltonian oxygen plus V, where we have equations in 34 7. In terms of nomenclature, we use V here to describe the coupling generically. For example, when the emphasis is less on a specific transitions and coupling and more on the exploration of generalizable dynamics, also we will at times use concrete examples such as electric coupling for the deuterium pattern for transitions as in equation 35. Later in this text, we will use the letter U specifically to refer to coupling for the deuterium helium-4 transitions. These distinctions in nomenclature is particularly relevant when rate estimates are developed. Sections 5.3 and subsequent sections, where we need to make use of concrete matrices elements that are characteristics of specific transitions and couplings. Now I want to go to another sections, which is excitation transfer as a result of second order interactions. Since first order processes cannot be resonant due to the energy mismatch between the nuclear systems and the oscillators, we are interested in the second order excitation transfer, which can be resonant. The first order interactions in the Hamiltonian can be replaced by second order interactions. For derivations of second order interactions, see section 6.4. The terms in Hamiltonian couple two states are resonance and near resonance with exchange of oscillator quantum above resonance by 23.84 mega electron volt, below resonance by 23.85 MeV, as well as above resonance by 47.7 MeV and below resonance by 47.7 MeV. To see this more explicitly, we can define the equations based on the 39, which then allows us to write the second order Hamiltonian as Hamiltonian tends to Hamiltonian 0 plus V minus we have another equations 1 divided by minus ionized E minus Hamiltonian 0 ionized V plus positive V 1 divided by E minus Hamiltonian 0 multiplied by ionized V plus ionized V 1 divided by E minus Hamiltonian 0 ionized negative ionized V plus ionized V 1 divided by E minus Hamiltonian 0 multiplied by V plus. The second order, for example, excitation transfer Hamiltonian based on the reference 81 includes coupling to intermediate states that can be massively off of resonance. Off of resonance in this context means that we consider the occupation of states that have more or less of the total energy available during the dynamical process. But since the process is fast, this is technically allowed by the formalisms. For focus on the most likely dynamics, the coupling that leads to term which double the excitations or double excitations, the first coupling terms in equations 40 are eliminated by restricting the terms kept in the Hamiltonian to focus on second order excitation transfer to off resonant nuclear states with single excitations or D excitations according to the equations 41. In other words, the scenario shown in Figure 8, while conceivable, is excluded from the modeling for proposed here since it is considered less relevant than excitation transfer via single excitation and de-excitation. The latter dynamics are illustrated in Figure 9. If the coupling is weak, as it is in our case, then the self-energy terms can be expected to be small. This suggests that the self-energy terms can be dispensed, which and focus is on the direct transitions by working with these questions in 42 and 43. Figure 8 illustrates excited deuterium and ground helium-4 nuclear states are coupled to a resonant nuclear state via a shared oscillator model. Atom-zero resonant nuclear energy transfer occurs through the temporary occupation of virtual states in which either more upper pathway or fewer lower pathway of the nuclear systems are excited. When there is more than one donor and one receiver present, as it is the case in the system we consider with many donors and receivers, shown here as an example are two deuterium donors and two helium-4 receivers, then double excitation and double de-excitation can occur. For the sake of simplicity, we do, however, exclude scenarios with double excitation and de-excitation from the modeling in equation 41. The resulting model is one that focuses only on terms responsible for neo-resonant excitation transfer. For example, the receiver systems matches the donor systems in energy via second-order indirect coupling through the traversal of off-resonance intermediate states, such as model will help move toward analyzing the current dynamics of interest. Figure 9 illustrates the excited deuterium and ground helium-4 nuclear states are coupled to a resonant nuclear state. So via a shared oscillator model, resonant nuclear energy transfer occurs to the temporary occupation of virtual states in which either both upper pathway or neither lower pathway of the two nuclear systems are excited. Note that due to the symmetry in the upper and lower pathways, destructive interference greatly hinders indirect nuclear excitation transfer. The upper and lower parts in Figure 9 represent a different off-resonance pathway between real states in the Hamiltonian via intermediate states, which are also sometimes described as virtual states in Hamiltonian matrices, such as intermediate states are represented through off-diagonal matrix elements. Now I want to go through the destructive interference and its reduction to loss and approximate evolution of the denominators of equation 42 leads to equations 44, 45, 46, and 47, as can be seen from the diagram in figure 9 from the corresponding simplified equation 47. The symmetry of upper and lower pathways causes destructive interference, resulting in an interaction terms of zero. In practice, this represents a localization effect where coupling would be dominated by nearest neighbor interactions, with the result of no or only very weak indirect coupling between the real states of a more distant nuclear. In practice, this would mean no or unobservably slow transfer rates to distant nuclei. This kind of destructive interference is reduced if the symmetry of the available pathways through the intermediate states is broken and certain pathways are removed or weakened. This is indeed the case when a loss selectively affects some pathways more than others. Related to this concept, the impact of dephasing and dissipation loss on coherent excitation transfer dynamics were considered by Pelenio and Hugla in reference 82, who found an enhancement of an excitation transfer rate due to interactions of closed quantum systems with a noisy environment. Consider again the case where 23.85 megaelectron volt is transferred from a deuterium molecule representing a highly metastable helium-4 excited state to a helium-4 nucleus. Helium-4 ground states via indirect coupling parallel above process. The intermediate states at the bottom of the diagram in figure 9 are off of the resonance by 23.85 megaelectron volt. Consider the situation where there are relevant loose channels available for the negative states on the lower part of the diagram, as depicted in figure 10, where the systems can dissipate 23.85 megaelectron volts to bring itself back onto the resonance and where such loose channels are not available for the plus intermediate states on the power upper part of the diagram. This is indeed how loose can affect such a system selectively because the basis state energy lies well above the energy eigenvalue. If the system is perturbed when one of the lower intermediate virtual states is occupied, the system can terminate at the minus one state, resulting in a transfer of the off resonance energy delta E from the oscillator to a loose channel. This kind of the mechanism was proposed in the Hagelstein 2002 in connection with the closely related problem of multiphonon exchange and model in the subsequent papers. So, for example, reference 84 in connections with excitation transfer. This was discussed in reference 85. The basic idea is that quantum systems behave differently on resonance and off of the resonance and decay channels can be very different in the intermediate states involved in excitation transfer due to their being off of a resonance. In this picture, off resonance loss was considered to be very fast since the final mode in the model under considerations couples to all of the nucleus in the lattice, potentially providing access to many loose channels. Figure 10 illustrates while symmetry present in the scenario in Figure 9 causes destructive interference and greatly hinders excitation transfer. We can conceive of a scenario where a form of idealized loose eliminates the bottom passways and reduce destructive interference. In this case, excitation transfer is much less hindered. In terms of physical mechanisms for causing this kind of selective loss in the mega electron volt range, nuclear disintegration of lattice nuclei was considered to be dominant based on reference 86, leading to the complete removal of all lower pathways and therefore the complete elimination of destructive interference. This kind of loss can be considered to be ideal loss with regard to the acceleration of excitation transfer. However, it was subsequently understood that it is not possible for there to be contributions from all the nuclei and the lattice of resonance, and this form of loose to lattice nuclei comes with its own form of destructive interference. In contrast to focusing on other coupled lattice nuclei, there are loose processes associated with the nuclei directly involved in the excitation transfer that don't suffer from this kind of destructive interference. Such a form of loose is described in more detail in section 6.5. The conclusion of that discussion is that it is possible to work with the conceptual simple picture of ideal loose that assumes a complete elimination of destructive interference via removal of all lower pathways in the diagram, and I applied a correction factor of 1 minus n to account for the imperfect elimination of destructive interference in actual physical systems per section 6.5. The correction factor derives from the loose-based asymmetry between the upper pathways and the lower pathways with coupling on constant u and coupling constant u prime is equal to n u respectively in figure 11. An estimate for this correction factor on the order of zero point 0.1 is given in section 6.5. The model simplifies considerably when the system enters a regime where loose rate associated with the overall system's tau is fast compared to the two-level system's energy 85. For example, when 1 divided by 2, h tau is much greater than delta mc to the power of 2. Now suppose that we augment the second order Hamiltonian equation 42 by including off-resonance loops for the terms that involve an energy excess in the intermediate states, then we would obtain as the equation 49. Figure 11 illustrates the complete elimination of lower pathways. In Figure 10 depends on a form of loose that is idealized in reality, while there are strong loose channels affecting the lower pathways. Section 6.5, the reduction of destructive interference is not complete. To account for the presence of loose in the lower pathways and the partial reduction of destructive interference, we introduce and represents the difference in coupling between states in the lower passphase U prime and the states in the upper passphase U. Note that we use here U to refer to coupling in the due temperature helium-4 transition instead of the generic V considered with the sections 5.3 and subsequent sections. Approximate evaluation of the denominators leads to equations 50 in the case of large loose pair, equation 48, destructive interference is eliminated and the Hamiltonian reduced to equations 51, where we have equations 52. In other words, in the presence of strong selective loose, there exists a non-zero indirect coupling between real states of different nuclear groups in the same oscillator mode, including distant nuclear. This indirect coupling enables excitation transfer. Finally, we recall that this indirect coupling is based on the assumption of it all loose. To get a physically more accurately result, we apply the correction factor per sections 6.5 based on the equations 53. For the sake of simplicity, we will consider the case of ideal loose for the remainder of these sections and not carry the correction factor 1 minus n through very expression. We point out, however, that it is necessary to apply it when determining numbers instead to match experiments, as is the case in the later sections of this text. Now I want to go through the resonance conditions averaging over the oscillators. We seek to further simplify the main Hamiltonian based on the equations 53 so that we can analyze excitation transfer dynamics in the subsections. We formally introduce the resonance conditions which assumes the donor and receiver systems in the group A and B have energy levels that are matched. This is the case in our example with deuterium and helium-4 nuclei, which represents the same physical systems in the different states. We will need to keep in mind these conditions later when considering excitation transfer across different species of nuclei, for example, between deuterium systems and palladium-ion systems, and discuss in sections 5.5 and onward. The electric field operator creates or annihilates oscillator quantum, which means that the model under these considerations couples to a state that involves a different number of quantum. This can be seen by expanding out the Hamiltonian of equations 51 according to the equations 54. This interaction involves the square of the electric field, which means that there is coupling between the states that differ by 2, 0, and minus 2 oscillator quantum. Since we are here interested only in the resonance processes, it is possible to eliminate the coupling to off-resonance oscillator final states by taking expectation value over the oscillator degrees of freedom yielding. Thus, the model that results is maximally simplified to include only resonance excitation transfer processes. Note that since resonance excitation transfer not net change in two-level system energy results, the two-level system energy is constant. Note also that since there is no coupling to off-resonance terms, of the oscillators, all of the basic states energies will be the same. This means that the Hamiltonian oscillators will not contribute to the associated current dynamics, and that we can work with the Hamiltonian of the form of the Hamiltonian is equal to 1 divided by delta MC to the power of 2 and so on. Equation 56 is now the simplified Hamiltonian, which describes resonant excitation transfer between sets of many two-level systems. Note that no self-energy terms are included as we assume weak coupling between group A and B. Now I want to go through the approximation classical dynamics from Ehrenfest's theorem. We can now proceed to explore the coherent dynamics associated with cooperative resonant excitation transfer between the two degenerate levels, as described by simplified Hamiltonian equation 56, as described by Hagelstein, reference 87. The Ehrenfest theorem can be applied as the derivative of the Q based on the time is equal to derivative Q time plus 1 IH and QH. Hamiltonian approximate classical evolution equation can be developed for the system. This yields to equation 59, 60, 61. Since these dynamics are related, simply it is possible to eliminate each triangular components and obtain these equations in 61. Nonlinear Rabi oscillations. Solutions to these equations are in general nonlinear Rabi oscillators based on the reference 88 and 89, in which occupation probability producially oscillates from the ensemble out to the ensemble way and back in a pulsed manner with a delay between pulses. It is possible to develop an analytic solution for single excitation transfer pulse of the sort under conditions where the excitations transfer from the ensemble A to the ensemble B, when the number of two-level state systems in the two sets A and B differs. Then we can write these equations. This results in a pulse lock increase and decrease of decay enhancement, whose shape is depicted in figure 12. The pulse length delta tau decay when the populations are mismatched is as follows, where absolute SR divided by H is the initial population of group. In our case, deuterium initially divided by 2. Note that for this highly idealized system that we have not taken into account decoherence or loose processes. So figure 12 illustrates illustration of the decay enhancement pulse in question 62. Minimum and maximum decay factor. Based on analytical solutions in question 62 and 63, we can estimate the maximum transfer rate tau maximum for a mismatched system to be on the order of equation 64. Minimum and maximum decay enhancement factors can also be derived from the pseudo-Hespin Hamiltonian equation 56, see section 6.12, for the derivation yielding the equation 65. Hamilton is equal to 1 divided by 2h omega alpha b square root SR multiplied by SR plus 1 minus MR minus 1 multiplied by MR square multiplied by square root SB plus multiplied by SB plus 1 minus MAB plus 1 multiplied by MAB, with the transfer rate tau is equal to omega b square root SR multiplied by SR plus 1 minus MR minus 1 MR multiplied by MR multiplied by square root SR multiplied by SAB plus 1 minus MAB plus 1 multiplied by MAB. We can define the decay enhancement factor Betzoid decay as Betzoid decay is equal to square root SR multiplied by SR plus 1 and minus MR minus 1 multiplied by MR multiplied by square root SB multiplied by SB plus 1 minus MA plus 1 multiplied by MAB. The decay enhancement factor assumes its minimum value at t is equal to 0 when the dynamics just start up. It then applies to the rate for the first transition. In this case, we can take MR as SR and MB as a minus SB, and the expression simplifies to tau is equal to RB square root 2 SR multiplied by square root 2 SB. We can connect with the number of deuterium molecules and with the number of ground state helium-4 atoms according to 2SR is equal to N deuterium 2SB is equal to N4 helium B, and of which tau mean is equal to omega B square root ND2 multiplied by square root and helium-4 for the minimum rate. For the second transfer, we can take MR is equal to SR minus 1, MAB is equal to minus SAB plus 1, which results in a rate tau mean plus 1 is equal to omega 2 square root ND2 multiplied by square root N of helium-4. For the N transfer, we can take MR is equal to SR minus N, MB is equal to minus SAB plus N. which results in rate tau mean plus n is equal to omega n square root n d2 multiplied by n helium-4. The decay enhancement factor takes on its maximum value when a large number of decay transitions have occurred. In that case, there is an additional enhancement of the order of NAD2 resulting in T maximum is equal to O1 divided by 4 multiplied by N deuterium deuterium square root Na deuterium deuterium multiplied by square root N helium-4 for the maximum rate. Now I want to go through the another sections. 5.3 transfer rate estimates deuterium deuterium to helium-4 nuclei. In the previous part, dynamic of excitation transfer were analyzed in the nuclear decay model, and it was found that excitation transfer in the form of nonlinear Rabi oscillations can occur between two ensembles of nuclei A and B that are cooked indirectly through shell oscillators modes. In the other words, excitations, or rather the occupation probability of excitation oscillates between groups A and B. In the subsections, a phase rate estimates is provided for this process. Continuing with the earlier conceptually simple example of deuterium-deuterium donor systems comprising group A and helium-4 receiver systems comprising group B. At the end of this section stands transfer rate estimates for excitation transfer based on each of the three coupling between nuclear and vibrational modes to be considered in this context: magnetic dipole coupling, electric dipole coupling, and relativistic coupling. Because of this structure, these sections also contain a quantitative comparison of these couplings, yielding the insight that relativistic coupling is substantially stronger than magnetic and electric dipole coupling. An overview of this particular case of nuclear excitation transfer is given in Figure 13, which shows explicitly the hindrances presented by the Coulomb barrier part of the interatomic potential of the deuterium-deuterium molecule, which is represented by the expressions with the gamma factor. Figure 14 illustrates the same process but emphasizes its time evolution, which includes traversal of resonance intermediate states per the discussion in sections 5.2. In the given case, the gamma hindrance factor comes into the transfer rate expressions twice: once due to the deuterium-deuterium molecule transitions to the helium-4 state on the donor side, and once due to the helium-4 nucleus transitions to the deuterium-deuterium molecule state on the receiver side. This is not the case in the faster nuclear excitation transfer scenarios explored later in this text. For the scenario here, we will see that while overall transfer rate is a function of several parameters and is therefore amenable to change and acceleration mode, so that the spontaneous fusion rate, the predicted transfer rate, is still too low to yield observable results. Nevertheless, the picture developed here will serve as an important stepping stone towards scenario of greater interest, which are predicted to yield observable results introduced and discussed in the later sections. When evaluating uptake rates for nuclear excitation transfer, it is important to compare them with expected decoherence times. If the mean transfer rate in a given system is longer than the corresponding mean decoherence time, then the system is unlikely to yield observable results at the scales typically qubits used in quantum computers, where the decoherence time is from microseconds to seconds depending on the technology used. All operate at temperatures close to 0 Kelvin. The case of coherence between nuclei is quite different. On the one hand, nuclei interact much less with the environment, which has to do with smaller size of their dipoles. However, since we consider nuclear systems across multiple atoms, such as in the case of nuclear wave functions of deuterium-deuterium molecules, special degrees of freedom, which include molecular dissociation and angular momentum change, has the potential to disrupt coherence. As shown in section 6.22, we expect a mean decoherence time of about 1 nanoseconds. Another decoherence mechanism is spin relaxation, which is, however, much slower than molecular dissociation. A proxy for spin relaxation in the systems of interest is provided by nuclear magnetic resonance experiments. In the study of deuteron spin relaxation in metal deuteride at room temperature, there are two time parameters of interest: T1, which is a measure of the longer lifetime associated with a spin correlation, and T2, which is a measure of the shorter dephasing time. A typical value for spin dephasing of hydrogen in palladium is 10 milliseconds at room temperature based on the reference 90. So we can expect the same order of magnitude for deuterium or helium. For now, we will adopt a decoherence time on the order of 1 nanosecond. And later sections 5.8 considers this kind of decoherence as an explicit constraint, which an excitation transfer process needs to exceed for it to yield observable results. In the sections, basic experimental parameters will be given under which the product transfer rate does indeed exceed the decoherence time. Sections 5.8 will build on sections 5.1, which contains extended variation of the model applied here. You see, figure 13 illustrates resonant nuclear excitation transfer of 23.85 mega electron volt from the deuterium tends to helium-4 fusion decay to the helium-4 tends to deuterium excitation. We consider two ensembles of nuclear and B, whereby ensembles all denotes the group of deuterium nuclei in the coupled systems which can undergo the deuterium tends to helium-4 transition, and B denotes the group of helium-4 nuclei in the coupled systems which can undergo the helium-4 tends to deuterium transition. The collective transitions of group L occurs currently together with the corresponding transitions in group B. Note that in actually this kind of excitation transfer process involves pathways to the different possible intermediate states which exhibits asymmetry in how they are affected by loss represented in the by n in figure 14. And I want to go to the figure 14. Figure 14 illustrates the resonance nuclear excitation transfer between a deuterium helium-4 donor transitions and a deuterium helium-4 receiver transition by indirect coupling via shade oscillator modes. A destructive interference between the upper and lower intermediate, for example, virtual states, is reduced by selective loss in the lower pathways, allowing for resonance nuclear excitation transfer to occur here, represented by N per section 6.4, recalling the expression for the excitation transfer rate. The derivation of decay factor in 6.12 yields expressions for the minimum and maximum rate of excitation transfer. Following equation 69, the minimum rate is as follows, where omega B refers to the generalized Rabi frequency for oscillating between the transitions in group A and B. Following equations 72, the maximum transfer rate is when a large number of transitions have occurred. The generalized Rabi frequency in equation 57 is such as here, where the notation wise we add here a subscript to V to highlight when a generic coupling is referred to rather than a specific one for the transitions considered. In these sections, as shown in figure 13, the generic coupling V generic is represented as a V generic is equal to U or is equal to U0 e to the power minus 3. Since, as we will see shortly, the gamma factor terms e to the power minus g can be explicated as a key factor in all of the indirect coupling terms in the sections where U0 differs based on the nature of the coupling, for example, electric, magnetic, and relativistic coupling. So thank you so much for watching my tutorial video until the end. Today is the 4th day of the July 2026, and the time is at the midnight. You can find any simulations which is related to nuclear fusion from my github.com/masterscript or github.com/kashi script or github.com/samurai script.